All right, I'm gonna go get my caffeine from my office. Oops. All right, daily quiz for DiffyQ is up. We pretty much will have until I get back from getting the caffeine from the office. It'll be about a minute or two. Because there's no calculations or anything like that you gotta do here. Just what's the answer? You know it or you don't.
I'm in class. The messages, read the messages. Read the messages.
Got 10 seconds. Stop share. There we go. All right, locking here in 3, 2, 1. So what can you do if you can't find the solution analytically? Use Euler's method is the only method you could probably use. No, there are a ton out there. You got forward Eulers, backward Eulers, central difference method. You can have other mixed versions of that. For those, you use Runge-Kutta methods, which are higher order approximations. You can use for first order, you can't really use any finite methods. It just all gets wrapped up into a class of methods called finite difference methods, which are all different ways to just approximate. So as long as you said Euler's method, because that's exactly what we talked about, or just said approximate it, that's all you need to do. So if you can't ever solve it analytically, you just approximate it instead. So other things, Kush, Shimona asked me this. I want to make sure I talked about it. One is the test for differential equations. It's test in quotes. not just Thursday, Thursday and Friday. Okay. So the way I do my tests for something like that, if it's not in class, is I make sure that it's available for either 24 or 48 hours. And so what's going to happen is, okay, share content screen. I'm trying to multitask. On Thursday at 12 a.m., you will see a link for the test appear. If you wanted to be up at 12 a.m. so you can download the test, you're more than welcome to. Okay. That link for the test in the place where you get to submit it will be available from 12 a.m. on Thursday up until 11:59 p.m. on Friday. You have that amount of time to get the questions, write them out onto your own piece of paper, solve them, clean up your solutions. Okay. Submit your final product. You can scan it. Is everyone familiar with how to use like something like Cam Scanner or Tiny Scanner, some app on your phone to turn documents into a PDF? Yeah, notes on the iPhone too. Even though I have a Mac, I really do Apple products, so I always forget about iPhones and whatnot. But I digress. You can use something like that to create a document. For some of you, I know having me for Calc 1 and 2, we had to do that the whole time for assignments. So the key thing here is, you're going to piss me off if you're having to upload multiple documents. Your submission should be a single PDF. Yes, you will probably have multiple pages, but each app, you can add multiple pages to a single PDF and upload a single PDF. If you are trying to say upload 5 different documents, one, you're probably going to accidentally, there's a high chance you're going to screw something up. You might accidentally upload the same page twice and not upload a page that you needed to, which means you missed an entire page of work, so your test grade is going to get screwed up. Okay. Cue is, if you're uploading more than one document, you should probably stop, make sure you can turn them all into a single one. Okay. Also, check your PDF before you submit it, please. It's something that should always be done, but especially if you're trying to rush at the end, or if you're just tired, you're like, I want to get to my spring break, this is the last thing I need to do. You just take pictures, you upload the document, submit it, you're done. Turns out I can't read half of it. What do you think is going to happen? You'd like to think that I'm going to be gracious too and not want to enjoy my spring break, and instead be tracking you down to make sure you actually submit, right? So yes, I will try, but I could also be a hard ass and just say, no, I can't read it, I can't grade it. Okay, so what's the easiest way to make sure that neither of us have to worry about that scenario? Yeah, just check. All right, make sure you're not missing any pages. Make sure everything's readable and what you want to actually submit. And here's the last thing with that, in regards to that. You have 48 hours. Really? It probably shouldn't take you more than 2 to 3, and that's if you're not well studied. Okay? If you're well studied, so I actually study before you start looking at the questions on the exam, and you're not going, oh, wait, I think I remember that. Let me flip through my notes and spend 30 minutes flipping through notes to try to figure out what you need to do. And then you go try to do it, and you have to make sure you just took a question that probably would have taken you 5 minutes to solve if you'd already looked at the information and remembered it, and you turned it into a 45-minute process. Okay. So even though this is a take home, still study. Because the more work you put in now, the less work you have to put in during that 48 hours when you have a timer. Just a good piece of advice. I found that it's helped a lot of people out. All right. So, and I guess we're looking at this broadcast. The last thing is I am going to consider that 11:59 p.m. a hard deadline. Okay, 48 hours is plenty of time for you to download. If for some reason even internet's being choppy at your house, get somewhere on campus where you can download the exam and then look at it, do your problems, and submit. Okay. If you are trying to submit the exam at 11:55 p.m. on Friday night and WAPA goes out and you're unable to submit, Don't come crying to me because I gave you 48 hours to do it. You were the one who decided to wait till the last minute and then ran into a terrible situation. Did I take the risk by you waiting until 11:55 p.m. to submit the test? I didn't take the risk. Who took the risk? You, the student, did, right? If you're trying to file tax forms and you're trying to make sure you're on the, or it's filed by the specific date by 5 p.m., right? They're not going to care if you got stuck in traffic and you showed up at 5:10. They're going to say, no, sorry, we're closed. And you didn't get to submit your test on time, you're going to pay some fee, whatever. Same thing here. I like to always spin little life lessons in because I've learned a few of those the hard way. Much easier to learn to deal with them in a classroom than it is outside, because that can cost you money outside. Also, cool, but any questions?
We have class on Friday.
Maybe. I haven't determined yet. Good question.
So today is gonna be the next.
No. No. So we're going to start into second order differential equations today. And that will not be on there. Right? Yeah, no. What was that? No, no bonus questions. Yeah, I'm one of the people who I don't believe in extra credit. So also that's your thing at the end of the semester. I'm asking for extra credit. I'm just going to tell you now. But I don't know. While we're on the topic, what do I usually do? Like, for example, daily quizzes. Drop 5 lowest daily quizzes at the end, right? Or you give me say, hey, I understand you're going to screw some things up along the way. No one's perfect. Those who are perfect, you just get a little bit of an extra benefit for being perfect. All right. However, I'm not going to make myself do more work because you decided you didn't want to do more work earlier in the semester. That's kind of the way I look at it. It's definitely very selfish of me. I'll 100% admit that, but also just tell you up front that's what to expect. All right, I think that's enough talking about me and the test. Any other questions? All right. Let's get into it. So we're going to, for the last half of the semester, really be working with what are called second order differential equations. We're going to start out with what are called homogeneous second order differential equations. So let's not use homogeneous yet, just say and we do try to be purposeful with our language and mathematics. So far, we've been dealing with first order differential equations, which means the highest derivative you're dealing with is what? First derivative. So if we're talking about second order differential equations, how high derivatives are we going? The second derivative. But when I say second order, that just means the highest one that I see is the second derivative. I can still have a first derivative inside of this differential equation as well. So second order differential equations are going to be something of the following form. So I can take the second derivative of whatever my variable y is with respect to the independent variable x or t, it doesn't really matter. I'm going to try to break this up, t being time, just any independent variable here. Usually in application though, it is time. So it's going to be equal to some combination of our independent variable x, the solution itself y, and the first derivative. It's called linear. I'm going to shorthand differential equations to DE. If that function, which is going to be a function of, again, the independent variable, my solution y, and the solution of the derivative y, is going to be something of the form so a function of x minus a function of x times y plus another function of x times the derivative. Linear in the terms of just the y, so the solution in its first derivative. So i.e. it kind of looks like an equation of a line. So in general, the second order ODE that is linear will be written as the following. So I'll have y double prime plus p of x y prime plus q of x y is equal to g of x. So then from this, we also have two different classifications. I already spoiled one, homogeneous, and the other one is non-homogeneous. Homogeneous differential equations are easier. And so we replace one of these terms with a zero. Which one do you think it is? What was that? Yeah, the g of x. So it's called homogeneous if g of x is zero. If it's not zero, then it is called non-homogeneous. And even with these, we can still define initial value problems. But one of the things is when I add in extra derivatives, I have to add in extra information. So an initial value problem for a second order ODE second order DE means conditions on both the function y and its derivative. That is, it's always going to look something like y double prime plus p of x y prime plus q of x y equal to g of x, where, whoa, sorry about that. Where I need to have two pieces of information. Now, we'll see where this comes from in a second, why this is needed. But when I add in a second derivative, I want to take this kind of calculus approach. I want to get to a certain solution y. To get rid of that second derivative, how many times am I going to have to integrate? Twice. But if I integrate twice, it means how many integrating constants am I going to get? 2. So I'm going to have 2 unknowns. And if I have 2 unknowns, I'm going to need 2 pieces of information to help figure out what those exact unknowns need to be. I want to find a unique solution. So if I added in a third order initial value problem, so I go up to third derivative, I would need 3 pieces of extra information. My solution Y is its derivative and second derivative. If I want to do a fourth order differential equation made into initial value problem, I need 3 pieces of information. Solution, first derivative, and second derivative, and third derivative. Yes, it's 4 pieces. Good. Okay, so let's get an idea of what these solutions are. We're going to start with a motivating example and just say, hey, can we get solutions, again, general solutions, and then see from there how can we generalize that process to more complicated differential equations. So first thing we're going to work for is still a linear differential equation, but instead of having maybe functions of x there, I could simplify them just to be what? We did this before. Don't make them functions that change, just make them what? Make them constant. Constants are easier to deal with, especially if I'm going to be doing integration, right? Just bring them out front. So let's start with a simpler version. I'm going to start with a linear second order differential equation with constant coefficients. And then we're also going to assume that it's homogeneous. Again, for simplicity, right? That is one of the downsides of differential equations. You get all these different classifications and it just starts making the names for these things really long. Homogeneous linear second order differential equation with constant coefficients. But it describes all of the different properties that we have written. So this is the first class of these second order differential equations that we're going to try to solve. But still, even without any idea of how to do this, that's still kind of daunting. So instead, let's try something else. Let's consider a very, very simple differential equation. So let's just take out that first derivative and say, okay, the second derivative minus the original function's got to be equal to 0. Which means when I rewrite this, this just becomes, I want to find a function whose second derivative is itself. All right, well, I could try to integrate both sides, but then I'll get a y is equal to a double integration of my solution, which means then that the function needs to be its own second antiderivative as well. So maybe there's not a direct calculus way to get it, but I do know of a function that will work. What function can I take the derivative of twice and get itself? Yes. I take the derivative of e to the x, what is it? E to the x, I take the second derivative. So get e to the x. Okay, well, e to the x is a solution. Because I'm having to take the derivative twice, that's not the only solution. Very similar to this one, but there's another function that also works. Ooh, cosine, good guess. But what is the second derivative of cosine? It'd be negative cosine. Similar with sine, second derivative of sine would be negative sine. Sine, cosine, cosine, negative sine. E to the negative x. Because what is the first derivative of e to the negative x? Well, it'll be a negative 1 times e to the negative x. So I'll take e to the negative x multiplied by the derivative of what's up in the exponent, that's a negative 1. But if I take the derivative one more time, e to the negative x. Because then I'll be multiplying by two negative 1s. So the negative times negative becomes a positive. So e to the negative x will also work. But then because of the sum or difference rule for derivatives, are these the only two things that are going to work? No. Any constant multiple of these functions will work. 2 times e to the x, just for example. I take the derivative of 2 times e to the x. Well, I'll bring the constant multiplication of 2 out front. I take the derivative of e to the x, and that's just e to the x. So I get 2 times e to the x. I take a second derivative, and it's still 2 times e to the x. Because it doesn't matter whether or not I make that positive 2, negative 2, positive 100, negative 100, positive pi, negative pi, whatever constant multiplication will work. So I can also multiply each of these two solutions by any constant that works, and then I can add or subtract. Technically, I'm letting the subtraction case be taken in by this constant, because if there was a minus here, I'd let the constant absorb that minus and it just turns into a plus. But any linear combination of these two would also work. Oops, it turned on me again. Because if I think about it, the derivative with respect to y, the derivative with respect to y of e to the x plus c2 e to the negative x, which is going to be the derivative with respect to y. Oh wow, I said y, x. Person only caught me there. So I take the derivative the first time, I will get this negative sign there. But when I take the derivative again, I multiply by another negative 1. The two negatives cancel each other out, leaving me with c1 e to the x plus c2 times e to the negative x. So we have a bunch of different solutions. What if we had initial conditions? So we're still considering the second derivative minus y is equal to 0, but then we say, okay, when x is 0, I want my y to be 2. And I want my derivative at 0 to be negative 1. Well, we just found out, hey, here's a nice general solution to that differential equation. And then I need to apply my two initial conditions. First one is just that, hey, whenever x is 0, I want the outcome of this function to be 2. So y of 0 equal to 2 means that I need 2 is equal to c1 times e to the 0 plus c2 times e to the negative 0, but anything to the 0th power is always 1. So I know that I need these two constants just to add up to 2. But then I need the derivative of this function at 0 to be equal to negative 1. What did we just say? Can we get it on the same screen? No, but this time I'll actually flip it purposefully. What was the first derivative of my general solution? C1 e to the x minus C2 e to the negative x. So this means I need my derivative to be negative 1, but that's going to be C1 times e to the 0 minus C2 times e to the negative 0. And again, anything to the 0th power is just a 1, so I have now negative 1's got to be equal to C1 minus C2. All right, how many unknowns do I have? 2, but how many equations do I now have? What was that? I heard G. Okay, 2. Good. So the equations that we need to solve is that I need 2 is equal to C1 plus C2, and I need negative 1 equal to C1 minus C2. So for those of you in intermediate calc 2, we kind of had to deal with solving solutions earlier today, especially for everyone. There's a couple of different ways you can do it. One is go straight to your linear algebra that you learned and use some of those techniques like row reduction, turning it to matrix, and do some factorization that you learn to solve a large system. This is only 2 variables, 2 unknowns. You probably don't have to do anything that crazy. What would you do to solve this system? All right, our substitution first. So let's do substitution. So what equation would you rewrite first, Xavier? Bottom one. All right, so just set it equal to C1. Cool. So that second equation that we have written there, oops, let me turn it so it's a little bigger. I can add C2 to both sides. That's going to tell me C2 minus 1 is going to be equal to C1. So the first constant is just the second constant minus 1. But then that gives me a relationship that I can then plug into the first equation. So then I get 2 is equal to minus 1 plus C2. So I subtract 1 from both sides. I have 2 C2s added together. And I get that second constant needs to be 1/2. All right, that means if the second constant is 1/2, what is the first constant? So I got to take this second constant, subtract a 1. 1/2 minus 1 is. Heard someone say it, but also heard a couple of different answers. Negative 1/2. Thus the solution to this initial value problem, y double prime minus y equals 0 with y of 0 is equal to 2. Y prime of 0 is equal to -1 is y of x equal to C1, so -1/2 e to the x plus 1/2 e to the negative x. That doesn't make sense. What did we mess up? Oh, I know what I messed up. What was the simple algebra mistake I made in blue? Should be 3, not 1. I'm subtracting 1 on the right-hand side, which means I need to add 1 to both sides. Now things should hopefully be looking better. Because when I take 3/2 and subtract 1, I get 1/2. So the actual solution should be 3/2. The second one, positive 1/2 for the first one. I think I saw a couple of you doing the same thing I was doing. You can always check, right? Easiest one was to plug in 0 to my solution, make sure it was equal to 2. And before it actually wouldn't have it been equal to 0. So if you make any small modification to this, just try to throw in a constant multiple somewhere, you're still going to see that your solutions are going to have kind of still the same general form. They're going to involve an e to the x and an e to the negative x. Okay, the question is, how can I combine them? And how can I generalize this observation to that second order linear differential equation with constant coefficients that is homogeneous? I think I got them all there. Yeah. Okay, well, keep it simple. Instead of just going straight to integration, let's just use these simple functions to build our solutions. And in this case, I'm going to do y is equal to e to the RT. Was that John? Yeah, kind of does. Is that better? No, you're right. That was my handwriting. All right, now we got the wordy part. Any linear second order differential equation with linear coefficients. What was that? Yes. This is how I'll do it. So what we're going to do is just consider that homogeneous. We'll get right up the start. Second order linear differential equation with constant coefficients. I'm going to assume that the solution's got to look something like this. Y times e to the RT. I know I might have to bring in a multiple because if I gone back to that initial equation instead of y double prime minus y, I did y double prime minus 2y. Something like that. For 4y, I'm going to have my solutions are going to have to be e to some number times my independent variable t. But one of the great things is, if I'm assuming I know the solution, I can plug it straight into the differential equation. Said y has got to be equal to e to the RT, so this means a times the second derivative of e to the RT plus b times the first derivative plus c times e to the RT. It's going to be equal to 0. Now let's break this down some. Well, that's just going to be some constant c times e to the RT. Let's work to the right. What is the first derivative of e to the RT then? Yeah. R times e to RT. Chain rule. It's going to see the function repeat itself. I just need to multiply it by, the derivative of the exponents. All right, that's the first derivative. What's the second derivative going to be? R squared e to the RT. All right, so then I want to rewrite this, so I drop the parentheses. A R squared e to the RT plus BR e to the RT plus C e to the RT, and that's got to be equal to 0. Wait a second. What do each of those have in common? So what can I factor out? E to the RT. Which means then this is going to be a times r squared plus b times r plus c times e to the RT. This has got to be equal to 0. And I go back to algebra. If I want to multiply two things and make it equal to 0, then either one of those two, I said either or, one of those two has to be 0. But what about e to the RT? Will that ever be 0? No. It's a function that is always above the x-axis. Always going to give me positive values, no matter what value. I'm using t for some reason now. But no matter what value of t I get. It gets really close to 0, absolutely. But it never actually reaches it. Which means, assuming that e to the RT is our solution, this is only going to be true if that little polynomial in terms of r, that a to the r squared plus br plus c is equal to 0. Well, then I'd want to solve for r. You think you could do that? Yeah, you are well past pre-calculus and algebra. If you've done this 100 times, you could do it a few hundred more. I could maybe try to factor. I know what a, b, and c are. I could use quadratic formula. I could complete the square. Whatever process I need to do, I could figure out what those values of r are. All right, so we know we can get them, which means that I know what my solution to the differential equation will be. But then I got to think back to, okay, solutions for quadratic equations. How many solutions can I have to a quadratic equation? Ooh, so I can have 2 real. That wasn't the only case. I could have two imaginary numbers. Or what? Not zero, but that's a specific example. It could only be one solution. You can have two real solutions, you can have one real solution or two imaginary solutions. When it came to quadratic equations, that was the three cases of solutions that you could always have in general. Which means that I have three cases for the solutions to this second order linear differential equation that's homogeneous with constant coefficients. Yeah, it's a mouthful. I have to say it a lot. You don't have to. Ooh, that'll be fun on Wednesday. Make y'all recite that. Yeah, we're going to do that. Anyway, this equation right here is huge. In fact, it's so huge we actually gave it a name. This is something called the characteristic equation. Because it's going to characterize your solutions to the differential equation. As we said, it'll be either two real numbers R1 and R2. Do those actually look like R's this time? Cool. One real number, just an R1, or three, two imaginary. Which we're going to denote with R1 star and R2 star. And if they're imaginary, it's actually okay. We'll kind of dive into this a little bit more. You can still get a real part of these characteristic equations that will work because if they are imaginary, we can use the following relationship. That is e to the negative I, or positive or negative I, is equal to cosine of theta plus or minus I times sine of theta. So just to note that that is a dealable case. It's not going to be a, oh, everything's bad. You can still get solutions from it. All right, well, we have the second order linear homogeneous differential equation with constant coefficients. We now know what the solution is going to look like. R1 and R2 are the roots of your characteristic equation. Well, that means in general, the solution to ay double prime plus dy prime plus dy equal to 0 is y is equal to c1 times e to the r1 times x. I'm going back to x instead of t. That is make the teaching moment of, it doesn't really matter what your independent variable is. Independent variable is just represented by whatever. But you should at least make sure they're matching up. Where R1 and R2. Solve the characteristic equation. All right, well, if we have the general solution to a differential equation, we can also apply any general boundary, or I said boundary conditions, any initial conditions. So then I know that my function at some particular starting point is going to have an initial value, which we'll call y naught. And that my derivative at that same starting point told myself I wouldn't slide into using t's today. And with that, while you give me this information, I can go ahead and find out what the solution is going to be to that initial value problem. Because I'm just going to end up turning this into a system of equations. What's going to happen here is I'm going to have C1 e to the r x naught, r1 x naught plus C2 e to the r2 x naught is equal to y naught, and C1 e to the r1 x naught times r1 plus C2 r2 e to the r2 x naught has got to be equal to y prime naught. Not a fun equation to solve, or system of equations to solve, but if you take the time to sit down and do it, I believe that every single one of you in here has the ability to, given there enough amount of time. But you're going to see that the constant 1 actually needs to be y naught prime minus y naught r2 all over r1 minus r2 e to the negative r1 x naught, and C2 is going to be something similar. Y naught r1 minus y naught prime all over r1 minus r2 times e to the negative r2 x naught. So overall, solution to a second order IVP of the form a y double prime plus by prime plus cy is equal to 0 with y of x naught being y naught, y prime of x naught being y prime naught is y of x is equal to y naught prime minus y naught r2 all over r1 minus r2 times e to the r1 x minus x naught plus y naught r1 minus y naught prime divided by r1 minus r2 e to the negative, or sorry, not e to the negative, e to the r2 x minus x naught. So as long as it's this nice simple form, we now know how to find the solutions. And it's all just from making that clever observation that for these second order differential equations that are linear like this, and do have simple coefficients, well, they're always going to be the form e to something times my independent variable, whether it be t or x. I'll leave them at the top. Let's put this into practice. So I'm not going to give myself any initial conditions here. All I'm doing is trying to just find the general solution. Okay. All I'm trying to do is I want to give us. Yeah, no. Actually, let me sit down over here. I think I was sticking up all up over here. All right. So I get to ask myself some questions. What is the order of this differential equation? Second order. All right. Is it linear? Yep. Does it have constant coefficients? Yes. Is it homogeneous? Yeah. So I know that to figure out the solutions, all I need to do is figure out the roots of the characteristic equation. So I know my solution will look like this, where R1 and R2 are solutions to R squared plus R minus 12 equal to 0. Taking it back, my characteristic equation was AR squared plus BR plus C, where A, B, and C were the constant coefficients for my second derivative, the first derivative, and my solution y in that order. I go back to my differential equation. What am I multiplying the second derivative of y by? Multiplying it by 1. Right? There's nothing there. Multiplication by 1. What about my first derivative? Y. Positive 1 again. What am I multiplying the y by? Negative 12. That's how I get my characteristic equation. 1 times r squared plus 1 times r minus 12 has got to be equal to 0. So I need to find the roots to this quadratic equation. Can I factor it? What will it factor into? R minus 4 plus 4. Definitely need a mixture of 4 and 3. So then what are the roots? And 4 and 3. Thus, the general solution is going to be some constant times e to the negative 4 times x plus some constant times e to the 3x. And this is the first time that we're doing this. Probably want to confirm that this is actually true. That this is the solution to the differential equation. Made sense in theory. If it held in theory, it should hold here, but it never hurts to check. So I take my solution, multiply it by 12. Or negative 12, that's going to give me a negative 12 C1 e to negative 4x minus 12 C2 e to the 3x. That's going to get the minus 12y part of my differential equation. What is the first derivative of this solution? So it'd be a negative 4 times C1 e to the negative 4x. Essentially just multiplied by the derivative of the numerator, which is going to be negative 4. But then plus 3C2 e to the 3x. Just making myself one little. What about the second derivative? What is that going to be? So if I take these together, y double prime plus y prime minus 12y is going to be 16C1 e to the negative 4x plus 9C2 e to the negative 3x. So I'm going to fruits, I'm going to drop down the next line, and I have plus the first derivative, which is a minus 4 C1 e to the negative 4x plus 3 C2 e to the 3x. And then when I do that minus 12y, that's going to be a minus 12 C1 e to the 4x, negative 4x, sorry, minus 12 C2 e to the 3x. What is this all going to be equal to? 0. If I take 16 C1 e to the negative 4x, subtract 4, and then subtract 12, well, the e to the negative 4x's cancel each other out. Similarly with the e to the 3x's. I have a 9 plus a 3, but then minus a 12. Overall, this is going to be equal to 0. And that's what we were looking for. So is this a solution to that general differential equation, second order linear differential equation with constant coefficients that's homogeneous? Yeah. So really all I need to do is figure out, okay, well, take the coefficients for that differential equation. Instead of putting derivatives, change it to r squared, r, and a constant. Find the roots for that characteristic equation, and I have my solution. Pretty simple. It definitely rested on a key observation, but once you make that key observation, not too much work to it. Any questions for me so far? There's one more case I want us to consider. I'll try to leave that green at the top. So this time, I'm going to consider second derivative of y, but now plus that function y is going to be equal to 0. Is this still a linear differential equation? Yeah. Is it homogeneous? Second order. Constant coefficients. So I could apply what we were talking about. But I want you to be careful. Let's not have to go there yet. We had a similar equation like this that we started with, our little motivating example. Difference was it was a minus y instead of a plus y. Which means I can turn this differential equation into what function can I write such that its second derivative is just the negative of that function? Sine and cosine will work. Those are two particular solutions, but kind of as we saw with the e to the x and the e to the negative x in the previous one, those aren't the only two solutions. We also have any linear combination. Wait a second. We said this still matches up with the type of differential equation we were talking about before. If I go back to that function and just say, okay, what's its characteristic equation? Well, the coefficient of my second derivative is just a positive one. So I'll get the r squared term there times the positive one. But then I don't have a first derivative, so it's coefficient 0. I have a coefficient for the y term, it's a positive 1, meaning my characteristic equation is r squared plus 1. And I solve this quadratic equation, and that tells me r has got to be equal to what? Either positive or negative, the square root of negative 1, right? Subtract 1 from both sides, take the square root. And anytime I take the square root, I have to consider two cases. But wait a second. Those are imaginary numbers, which means characteristic equation tells me my solutions or y is equal to some constant times e to the negative ix plus some constant times e to the positive ix. So I have this conundrum. These are all my solutions to that differential equation. But then we said, based on the theory that we just built, these are the solutions to my differential equation. Is this an issue or a non-issue? Got an issue? So I wrote a relationship when I said if we get imaginary roots. What was that relationship again? E to the plus or minus I times theta is equal to what? So I have this, which means I can replace these e's with this combination of sine and cosine. So we're going to actually get y is equal to C1 times cosine of theta. Let's see, I did minus first, so minus I sine of theta plus C2 times cosine of theta plus I sine of theta. And then I distribute the C1 and C2s through and I group them all together. It's going to give me a C1 plus C2 times cosine of theta plus, what was it, I? Let me make sure I get this right. Yeah. So then I get these constants. But this is differential equation. If I take any two constants, they add up to be what? A constant. And even though I'm going to be multiplying by that imaginary number, it's still just going to be some other constant C2. So kind of just ignoring for the moment the fact that there is this imaginary number I buried into this special constant C2 star. Is that just the same solution that we had before? Yeah. You know, someone would have told me. It's not my fault at all. Replace those thetas with x's so your independent variables match up. So we still have the same solution. So what this tells us is that we have two different ways we can always build these solutions, right? We can either do it with sine and cosine, or we can do it with these exponential functions. Either way will work. Question is, which one do you think we'll choose? Good guess. But at least for this class, no. We're going to go with e's. E's are a little bit easier to work with. So technically, we can use either sine and cosine, or e to the plus or minus RT or Rx to build our solutions. But we're going to stick with the e's. And I'm not really going to go too much because I got 1 minute. That's where we'll end it for today. Let me do that so you can get more of the info if you want it. So my usual spiel at the end of any class. If you have questions for me, feel free to stick around and ask them. Okay. Otherwise, feel free to get on out of here. Enjoy the rest of your Monday. And I will see you on Wednesday where we will pick this up. What's
Can
up?
you make it bigger, please?
Not this way. What part of this do you need? Last view. Better?
Yes, thank
Yeah.
Right off to the plug while you write the full process of the charges.
This one
Above,
above that.
yeah, right there.
Oh. Oh, wait, yeah, I forgot about the delay. Yeah. All right. Oh, yeah. Should stop the recording.